Alright, let's assume that the recording's happening. Alright, so centripetal acceleration, and this is maybe like the first new thing for grade 12. Let's just make sure that we got the lights set good. There we go. Alright, so when we say in linear motion is this default thing, it was probably like the first equation that we saw in grade 11, which is delta D over delta T. And we can put arrows over top because it's a vector, but I think we're just going to like hold ourselves back from that for a minute. With circular motion, the analog would be V is equal to, well, think about it. If I go from this point here and I go all the way around back to that same point again, that would be the circumference. So 2 pi r would be the circumference around the outside of that circle for centripetal acceleration, if that's a thing. And I think most of us kind of believe in centripetal acceleration because we've heard of it before, and anytime you take a turn, you can kind of like feel something funny happening when you take that turn. And then instead of the delta t, we talk about the amount of time it takes to make that complete cycle. So that's the period. And where we've seen that before is in sound and waves. We talked about like the periodicity to something repeating a cycle. But in this case, it's like literally a circle going around and around. So this is our analogous equation for the speed equation from kinematics. Just keep in mind that that capital T is period, and the 2 pi r is the analog to, distance, but it's the distance around a circle, so circumference. And when we talk about period, again, it's the same definition as we had from the sound and waves unit. We talk about the amount of time that passes divided by the number of cycles that occurs. So the number of times it goes around that circle, or the number of times in waves that the wave repeats itself. And if we're talking in units, we say, okay, well that's seconds, but then this doesn't really have units. Maybe we'll even make a note of that. No units. And the reason it doesn't have any units is because it's just a count. And anytime that something is just a count, we could also say that things that are just counts, those integer counts, does not contribute to sig figs. I mean, imagine if it did, like if the n value was 3 or something, automatically any period value would have a sig fig of 1, right? Because you'd be counting like a single digit integer. So that's one thing to make sure that we have in mind. Anyway, the frequency is just the inverse of that, the reciprocal, I should say. N over delta t, and we could write it as frequency is 1 over period. And just, we'll put it in writing, that delta t, is time to complete multiple cycles, and the n is number of cycles completed. And sometimes people say, okay, well, so this would be like the speed, right? How would you talk about the velocity for circular motion? And really, like, we got this little sketch off to the side here that I really stole from either a website or a textbook. But at any given moment, I would have an object that's going around in a circle, and that object going around in a circle would have, at any given moment, a velocity that's tangential to the path around the circle. So, at moment 1, it would have this velocity, moment 2, it would have this velocity, moment 3, it would have this velocity, always tangential to the circle. And then the topic always comes up of, whoa, how about centripetal acceleration? That's what we were trying to get to here. Well, first we had to talk about speed, then we had to talk about how it relates to circles, then we're going to talk about the directionality issue, like the fact that if this really is not just speed but instantaneous velocity, it's going to change depending on where you are in the circle, it's tangential. And then we get to the idea of acceleration. Well, acceleration is the rate of change of velocity over time. And the velocity, of course, has a direction because it's a vector. We've talked about it in terms of like linear motion, and this is how we've expressed it in linear motion. But if we were going to talk about it in circular motion, I'm just going to put out just a few equations that are going to be ones that I'm going to ask you to trust me on, okay? Because the derivation of them is a little bit beyond where I want to go with our math skills right now. And sometimes that's just the case. So it's going to be a little bit of a trust issue. But when we talk about centripetal acceleration, usually the first one people get introduced to is v squared divided by r. And if you wanted some, I don't know, like, we don't take away some of the blindness to this trust, if you wanted to have some sort of an idea that, yeah, this really is the case, if I take a look at the units, then the units would be, remember it's meters per second, but meters per second squared becomes meters squared per second squared. And then if we divide those units by meters, which is from the radius, then the squared would cancel and the meters would cancel, and we would get units of meters per second squared. So like from a basic unit analysis, dimensional analysis, I'm not going to say that's like a proof that this is the right formula, but anytime we can do dimensional analysis and the units work out, then it gives us some pretty good, well, lucky feelings that the units are going to support that this is a good equation, okay? So we got this equation 2 that I want to bring back to our attention, which was from the top of the page, so 2 pi r divided by period. And if we look at the units on this one, again, just to make sure we're good with this, we've got meters per second, and the 2 pi doesn't contribute to the units at all, right? Because there's no units associated with pi. If you wanted to go even further and say, hey, I want to sub this equation into this equation, oh my gosh. Now we got a situation where the 2 pi r is going to be squared. Notice that if I have 2 pi r over period squared, then that's going to be the r squared, so that's going to be the meter squared, divided by the second squared again, because the seconds is going to come from that guy. Well, that's exactly what we had over here, divided by the meters, and we get the same story that I was telling in the left-hand margin, but it's still going to end up being meters per second squared. So no matter how we deal with this, whether we deal with it as equation 1 on its own, equation 2 on its own, or equation 2 submitted into equation 1, it's all going to be good. Okay, so there's this nice unit consistency. Anyway, if we do sub equation 2 into 1, which is what I actually do want to do, then we end up getting AC is equal to 2 pi r over period squared divided by r. And then that's going to end up being, I'm not going to write it as an equal sign, I'm just going to do it as like a horizontal continuum. That's going to end up giving us 2 pi r times 2 pi r. I'm just going to expand out in full over period squared. That whole thing divided by r. And then really that's an r over 1. So I'm going to invert and multiply. And I can say, okay, well that means I've got 4 pi squared times r squared over period squared times 1 over r. And I'm inverting and multiplying that denominator fraction. But then that's going to allow us to cancel out the r. And then that finally gets us 4 pi squared r over period squared. So we got the second equation for centripetal acceleration, where we sub in that definition of circular speed into the gifted centripetal acceleration equation. We get 4 pi squared r over period squared. And we can also say, hey, since, as we said before, 1 over period is equal to frequency, we could say AC is equal to 4 pi squared RF squared. So I guess we really have like a fourth equation there, where we've subbed in this definition of frequency period relationship into this guy.